Hi everyone, this is Yukabuka and welcome to my home on YouTube. In this video, we will look at what per CPU variables are and how they are used in the Linux kernel. Before we dive into the actual implementation of per CPU variables, let's try and understand the motivation behind this specific feature. Typically, if you have a global variable within the kernel, then that global variable is accessed by, or technically can be accessed by, any kernel thread. And this kernel thread could be running on any of the CPUs on the machine. However, on the other hand, if you have multiple threads and each thread has its own kernel stack, then the local variables are allocated from these kernel stacks, and as a result they are local to that specific thread. However, there are some cases where you need a way to specify that there is a specific variable for which there are multiple copies, and each copy corresponds to a CPU. An example might be to use a variable that denotes the CPU number. As each CPU would have a different number, we would need the variable to contain different values, while at the same time the code should be able to access the CPU variable and figure out which core the code is currently running on. And this can be accomplished by using what is called a per CPU variable. Imagine a per CPU variable named CPU, such that there is a copy of this variable for each and every CPU on the machine. And each CPU would have stored in that variable its own CPU number. And this could happen during kernel initialization. So we'll look at how the functionality is implemented. We'll go through the theory first, and then let's dive into the source code. On the right side, I've opened a couple of links that I found while searching online for documentation on per CPU variables. One is a question on Stack Overflow, and the question is, how are per CPU pointers implemented in the Linux kernel? And we will be going through this answer here. And the second is this post on a blog which has this very interesting picture, and we will get to that later. The name of the blog is thinky.blogspot.co.uk, and it's a post from 2014. Okay, so let's start by looking at this answer here by Ugoren. Okay. So what he says is that normal global variables are not per CPU. Yes, automatic variables are on the stack, and different CPUs use a different stack, so naturally they get separate variables. Fair enough. It's not, though it's probably worth mentioning that it's not different CPUs that use a different stack, it's different kernel threads running on different CPUs that use different stacks. He mentions that most of the magic is implemented in percpu.h. Right now, I am in percpu-defs.h. Let's have a look at what files are there related to percpu. I see that I see the include ASM generic file, and I see a couple of other files as well, which are in include trace events. That's probably not the one we are interested in, but anyhow, let's take a look at what we have here. So there's an extern unsigned long per CPU offset of number CPUs. Okay, so that is an array of size equal to the number of CPUs. So let's say that we have 8 CPUs on the machine. The size of the array underscore underscore per CPU offset would be 8. Sounds good. And then we have a macro per CPU offset of x, which effectively dereferences underscore underscore per CPU offset of x and returns the value. So I guess it would be safe to say that the CPUs are numbered 0 to nr underscore CPUs minus 1, and that x is a CPU number. I guess that would be the case. Okay. And then you have a macro defined per CPU with a type and a name, and I believe this would be the way to define a per CPU variable. We can look around for an example for this. Let's say define per CPU, and yes, we do see quite a few of these. Let's go with this, and that's kind of expected, but we see that quite a few per CPU variables are being defined in various locations throughout the kernel. In this specific case, what we have is a specific CPU variable is defined and a value is being set to it. We can see that the arguments to this macro are a type and a name. So over here we see a hash define per CPU type name, and we have this specific line that is underscore underscore attribute underscore underscore section of data dot per CPU. What that line says is that once you compile the kernel, introduce a variable of name per CPU name into the section by the name of .data.percpu. Now, it should be worth mentioning that this is not where the actual memory allocation is performed. This is the variables in this specific section simply denote that there is a per CPU variable declared. It does not mean that the address corresponding to the variable within the section is the address of the per CPU variable. Okay, so effectively what it says is add this variable into the specific section, and such that the type is type and the name is per underscore CPU underscore name. This is the concatenation operator within a C macro. If you don't know, a hash will do that for you. And after that, what we have is a comment saying var is in a discarded region, offset to the particular copy we want. I'm not sure what that means, but let's take a look. I assume this specific macro is to retrieve the value of the variable of the specific CPU. So if you pass the value 1 as CPU, then it will return the per CPU value when running on CPU 1 for var. Okay, that sounds good. And then there is something a bit weird, that is star reloc underscore hide. I have absolutely no idea what that is. And in any, okay, we'll go into that later. But we can see that there is a dereference happening here to whatever is returned by reloc underscore hide. Apart from that, we have two arguments to that. One is the address of the per CPU variable, and the second is the underscore per CPU underscore offset of the CPU number. So I guess it's effectively calling per CPU offset of the CPU value. Right, that sounds good. And we also have a macro called underscore get CPU var of var, which effectively does per CPU var and SMP processor ID. I believe SMP processor ID will return the CPU number. So that's what can be used to get the value of variable for the current CPU. Okay, that sounds good. I also recall reading some documentation somewhere that per CPU macro makes sure that the current task is not preemptible. Hopefully we will run into this as we go into the source. And this is important because we do not want the task to change, or we don't want the task to pause and be scheduled to run on another CPU while it tries to figure out the value of a per CPU variable. We want to make sure that it continues running on the same CPU, and as a result the per CPU macro disables preemption for a while before reading the CPU variable value and re-enabling preemption. We probably will see that as we dive into the source code. I have a feeling that this is a cleaned up version of the code with some edge cases removed. Okay, so over here there is a description of what the reloc underscore hide macro, I'm guessing, does. The macro reloc underscore hide simply advances PTR by the given offset in bytes regardless of the pointer type. Okay, that sounds good. So effectively what it's doing is it's this pointer value plus the offset which is stored inside this array. And because the offset would be different for different CPUs, you would be able to store different values corresponding to different CPUs. Right, okay. Yes, that does make sense. So we've pretty much understood what this piece of code does, but let's quickly read through the entire answer. What does it do? When defining an integer per CPU X is created in a special section. When the kernel is loaded, this section is loaded multiple times, one per CPU. This part of the code is not, this part of the magic is into the code below, above. That sounds good. The underscore per CPU offset array is filled with distances between the copies. Supposing 1000 bytes of per CPU data are used, per CPU offset of n would contain 1000 times n. Okay, so this is assuming that the different copies are stored in a contiguous manner. So for example, all the per CPU variables of the first CPU followed immediately by the per CPU variables of the second CPU, followed immediately by the per CPU variables of the third CPU, and so on. So if there were 1000 of those, then per CPU offset of n would give you the offset into the nth chunk of per CPU variables, or that's what I understand from it. Right. The symbol per CPU _ x will be relocated during load to CPU 0's per CPU x. Okay, I guess what they are saying is, suppose the name of the variable is x, you will have a per CPU variable by the name _ CPU _ x, and in order for this to work, you need this to point to the per CPU variable of CPU 0, so that when you add a specific offset to it, it gives you the per CPU variable of CPU n. Okay, that sounds good. And then finally, _ get CPU var of x when running on CPU 3 will translate to star relog _ hide of ampersand per CPU x, okay, this is of CPU 0, plus per CPU offset of 3. In this case, it should be 3 into 1000, which is 3000. And that address is dereferenced. Relog hide effectively just adds the 2, and then the star does the dereference. This starts with CPU 0's x, adds the offset between CPU 0's data and CPU 3's, and eventually dereferences the resulting pointer. Alright, that makes complete sense. That's great. So kudos to the person who's answered this question. It's an excellent description. And now let's take a quick look at the other diagram that we have here. Yes, so we see that we have the per CPU offset for different CPUs stored within this one array. What we do is we get the address of one variable, say x, and fetch the offset value of the specific CPU, add that, and jump into that location. So let's say that we are trying to fetch the address for per CPU variable number name x for CPU number 2. First, we get the address of x within we get the offset of x within the range of per CPUs for CPU 0, and then we fetch the value of _ per CPU _ offset of 3, and we add the two values and dereference it. That's how we read the value of x for CPU 3. Okay, that sounds good. So let's just take a quick look at the source code. We are told that it's inside ASM generic, so we'll go to per CPU offset. Okay, and yes, we see that it's effectively just using the array over here, and the array over here is this. Yeah, and there should be a define per CPU somewhere. Define per CPU, and we see that here. and it jumps to CPU define per CPU section. And I guess there are a few levels of indirection here before we can get to the state described here. So we have so the attribute section part is the same as over here. The per CPU base section, it will eventually resolve to the .data.percpu string, and there is also the option to specify a name for the section which gets appended to the end, but we can see that an empty string is passed here. So I believe it is possible to create a per CPU section within a different section name, though I'm not sure if it's used within the kernel. And what about this? I'm not sure what that is. Right, so this is essentially the crux of it. Let's just check something real quick. What does that refer to? I'm not too sure. It's within compiler types.h. There's something over here that may or may not be defined, I guess. There's just one definition of that. So ignoring this and this, which essentially seem to be defined to nothing, we are left with this, right? And once we go back, this is, I'm not sure why there are so many levels of indirection, and we finally have this, which is what we saw on the Stack Overflow answer as well. Okay, that sounds good. Let's take a quick look at the percpu macro, and we see that it's slightly different in the kernel version that I have. We see that instead of the star reloc_hide macro, we have a star percpu ptr, which effectively does the same thing, though. It does an ampersand of var, comma, a CPU. Right. Interesting to know that the naming convention used is no longer per_cpu_ variable name. It's just the variable name. So let's try diving into percpu ptr. So the arguments to that are going to be the address of this specific variable and the CPU number. And we can see that whatever this macro resolves to is dereferenced. So let's just jump into this. We see that there are two of these. Go with the first one. Okay, so we have a pointer and a CPU number. The CPU number is eventually resolved to the offset using the percpu offset macro, and the PTR is effectively added to that. The shift percpu PTR does have a comment section above it that says add an offset, but keep the pointer as is. Use reloc_hide to prevent the compiler from making incorrect assumptions about the pointer value. The weird cast keeps both GCC and sparse happy. Okay, I think there is, I'm not sure what the problem is that arises from not using reloc_hide, but yeah, it apparently needs to be written this way. And as you can see, reloc_hide effectively converts PTR to an unsigned long and then adds offset into it and sets it back to the proper type. And that's how it accomplishes to advance P by an offset number of bytes, regardless of what the type of P is. That's kind of interesting. It's kind of interesting to see how it does that, especially this part here, the type of C extension. It's a GCC extension, I believe, and what it allows is, given a pointer, type of pointer will resolve the type of the pointer for you and place it over there, so that eventually when you return the value, it will be of the appropriate type. Okay, so we can go back, and yes, sounds good. Let's look at a usage of this function though, because I'm curious to see a usage of this specific function. Okay, let's try this. Yep. Yes. So we have percpu of frequency underscore scale comma I is equal to scale. Got it. All right, that sounds good. The value is being set in all locations. In some places it's being returned. Okay, sounds good. I did mention earlier that percpu would perform a preemption disabling, but we did not see that in the source code. Right now the code that I have indexed is for ARM. I'm not sure if that is the reason, but I most certainly did read some documentation that suggested that preemption would be disabled. Let's take a quick look at the comments here and see what's going on. Okay, this just seems to be a bit of a clarification, but does not answer our specific question on preemption. Okay. So there are two things that would be nice to check out. That is, let's just search around. That is percpu variables and preemption. Okay, we have some documentation here. Let's take a quick look at this. Okay, this seems to be a patch diff. Let's search for preemption. Okay, this means that there are no atomicity. Oh, but this is about this CPU. Okay, in the case of this CPU, there isn't apparently a necessity to disable the preemption or the interrupts. The CPU operations add a percpu variable offset to the processor specific percpu base and encode that operation in the instruction operating on a percpu variable. Right, okay, so this seems to be a very specific case of percpu variables. I don't know if this would apply for any percpu variable. Okay, so I can't find the documentation on the on the preemption. If you see something, please let me know in the comments. Let's see. Let's have a quick look at this documentation. It's documentation by Christoph Lemaitre. Okay, this makes sense. Sure. They're talking about atomicity. Okay, they have an example. Aha. Over here they have a preempt disable and an enable. And let's see. This doesn't specifically. Would not be good if preemption happens in the middle of the critical section that modifies the percpu variable, right? And as a result, you have these macros. So a get CPU var macro to get the current processor's copy of the data, and call put CPU var to current processor's copy. Right, so get CPU var returns the value and disables preemption. Put CPU var saves the value to the processor's copy and disables preemption. Right. Another processor's copy can also be accessible using the below command. I see, right. So if you're using okay, now it kind of makes sense, because if you're using per underscore CPU of variable comma, say a CPU ID of 5, then it doesn't really make a difference of which CPU you are running on, because the value of the per CPU variable returned will be of CPU 5. However, if you're trying to retrieve the value of the per CPU variable corresponding to the CPU that you're currently running on, then it makes sense to use macros such as get CPU var and put CPU var. And that's when preemption is necessary. Okay, that I think that makes more sense. So if you go to get CPU var, then we see that it does this thing where you have a preempt disable, and then it returns the CPU's &var. Okay, let's take a quick look at the CPU. Okay, this seems similar to what we had earlier. We just use something called my CPU offset, which is a per CPU offset of SMP processor ID. Okay, so if you go there, so what happens with shift per CPU PTR is it advances PTR by my CPU offset number of bytes, right? And where PTR would be the address of the per CPU variable for CPU 0. And my CPU offset is computed as per CPU offset of SMP processor ID, that is the current executing processor's ID. So it returns that value and we're gold. That sounds good, makes sense. Okay. Now I am curious about where the multiple sections for per CPU variables are created. That is, where multiple versions of per CPU variables are loaded into memory. So I will find that and make a video on that soon. But that's it for this video. In this video, we've looked at what percpu variables are, how they are implemented, and how you can define and use percpu variables. Hope you've enjoyed the video. If you have, hit like and subscribe. Thank you.